Good morning, my physiologist friends. Here we go. We're going to just chat for a while on specific immunity. We'll see how far we get before I decide I'm done and talking. And then good for you that it's Friday/Thursday Friday. Last day of the week. We are going to get together and quiz on some of this next week. But you know what? Part of this weekend is just, or part of having that day off is to take a mental break and stuff. So make sure you're taking that healthy mental break. That doesn't mean quit stuff. If you're really bored over the weekend, or actually I should say this, over the weekend, if you've got enough mental health and whatever, and we're only talking a little immunity here, especially if I hope you're finding it interesting, read a chapter or two of polio. There are certain things with specific immunity and stuff that we're going to talk about here that may trigger an interest in doing so. Anyhow, here's where we're at. We've talked about first line of defense, which is skin barriers, mucus, bactericides, and everything to not let pathogens in. Then we talked about the second line, which is the innate stuff. If stuff does get in, what's the general stuff that it doesn't matter what the infection is, that it's going to surround macrophages, protein complement, things that work as opsonins, the complement and interferon and stuff that surrounds it, and really are kind of a signal and a stuff. Natural killer cells, which get included sometimes in the third line, even though they're innate, but because they poke holes in and wreck the integrity of the invader, they get sometimes included in specific immunity with B and T cells, not that they're specific, but just because they have a similar function. And those are all general, regardless, the inflammatory response of everything rushing in and causing localized little edemas and swelling with vasodilation and blood flowing in and raising temperatures, etc. That stuff is all there. Working in concert with that then is that third line, that specific immunity. And this is what we're going to talk about. And I am going to leave you a question right now that I want you to ponder over the weekend, because you've heard of it if you've been watching the news, and this has been stated a lot. And for example, Sweden, I believe that Sweden has not done a stay-at-home thing. They are banking on something called herd immunity. Okay. And so here's the thing I want to look up for a conversation we'll have next week that goes along with all this. A, what's herd immunity? B, what are requirements for herd immunity to work, to function? And C, do you see any issues with, say, and you can read some articles or find some news clippings on what's going on in Sweden as opposed to its neighboring countries, and why are people, and who's talking about herd immunity, and is this something that is coming from experts and physicians, or something that people unfortunately think they may know too much about or whatever? But just get some background on that and see why or why not that may not function here. Anyhow, the third line then that works and helps trigger, and they all work together stuff, is then that specific immunity. And in your packet, you worked on two types. You worked on basically humoral or antibody-mediated and cell-mediated with T cells, and we'll kind of get through most of that. But anyhow, let's start here with my face in the way. Anyhow, specific defenses are those coordinated activities of T cells, B cells, antibodies that produce immunity, in the sense that as we're going to talk about with passive and active and whatever, first time infections, second time infections, you're hearing a lot right now about antibody testing, seeing who had it, whatever, and that's what we're going to get into. Certainly the second time you've been infected by something, your body can respond faster because it's seen it. Okay. This is specific resistance against potentially dangerous antigens that will infect your body, and they go directly towards, I'm going towards, this is what I do, whether it's the flu virus, HIV virus, right now, coronavirus, etc. T cells are really the cell-mediated immunity. B cells are the antibody, but they work together, and you're going to see that B cells activate T cells activate B cells, and whatever, it all works. Okay. It's just really a method of how are they activated, and they're both activated very similarly. T cells are activated by something called antigen presenting cells, which is really what happens when macrophages engulf stuff. And then they pop out those MHC. We talked about that with cancer cells, and those MHC, and how, you know, cancer cells didn't present with that MHC binding, and so your body knew, you know, that those were cancerous cells. Where B cells really are humoral, pathogens and antigens in body fluids. Anyhow, some properties of that immunity you build is specificity. T cells and B cells bind only one antigen. Now, part of that is then, do you have millions of these different things? Not really. You keep small amounts of memory B cells in. We'll see it as we talk about it, how they get there, you know, how long they last. Some B cells, memory B cells of infection, and others, it depends. But you keep small amounts around, and you can activate very quickly when you get infected with something. The versatility, there's millions of different lymphocytes, each sensitive to a different antigen. Memory cells remember the antigen, so you get that faster future attack. And again, I'll say it right now. The first time you're infected with something and you need to make antibodies, whatever, get that specific immunity going, you've got about, on average, a good 2-week time before antibodies are really built up and at the point where they're helping you. And that is where some viruses become very dangerous and very fatal, because if their action in your body, if what they do, if the toxins, the illness, the whatever, the infection that they spread can become very widespread within 2 weeks and really get your body going septic or beyond what antibodies can do in that timeline, then you are going to succumb to that deal. And that's that 2-week timeline of some of those infections are very rapid, very dangerous to your body because of that timeline. Others, you know, you may not feel great, whatever. And if you think of coronavirus now, they're talking about the big variety in symptoms that some people never even knew. The second time, you're looking at antigens being at peak within max 3 days, so 1 to 3 days. And so that's the idea. And this is the whole reason for vaccination. And then, of course, the tolerance of recognizing, unless you have an autoimmune disease, your normal self. Okay. All right. So macrophages, phagocytes activated by antigen exposure, stimulate specific immune response, just like everything. It's all like chemotaxis. What's going on? I've got the innate general defenses going, and whatever trigger response, antigens or fragments of those antigens, those pathogens must appear in plasma membranes. And that's where, when we talk about T cells, we'll talk about antigen presenting cells, because the macrophages engulf, and then on their membrane, they pop out those MHC type stuff, so that they pop out those antigens so antibodies can bind, T cells can bind, so they know that this macrophage is surrounding has been infected, and make that recognition. Okay. Now, what are antibodies? They're a Y-shaped protein. Okay, and we talk about antibodies, but specifically, what we're looking at are what are called immunoglobulins. That's the fancy term for antibodies. Anyhow, it's just a Y. You're going to see a picture in a minute. Couple of chains, having a light chain, big protein, polypeptide. Okay. There are some constant segments on that. Okay, on heavy chains form the base of the antibody. Variable segments, free tips, or antigen binding sites. So at the end of the Ys are the variable portions that are made that can grab onto those antigen presenting sites and hold on to. Antibodies themselves are not destructive. They don't do the destruction. Essentially, they're signaling molecules. Okay. And they hold on, and that's the trigger for other stuff to come in and do, both the macrophages, killer cells, cytotoxic or killer T cells, and stuff to come in and do the job of destroying that cell, that pathogen. And so that variable, that antigen, and that's why initially it takes a couple of weeks for your body to develop these antigens or antibodies, is to have those free sites so that you have those specific binding sites that it can grab that pathogen with. And that's the differences in the protein. And there's your picture. You can see here's, the heavy chain base, whatever. Here's the light chain, but this is the antigen binding sites. And you can see here's my antigen, little cartoon, and those ends of the Y grab it. And these are the variable segments here that are shown in yellow-ish that takes the time to make, and then they grab around, and that's a signal to come and kill. Okay. When they do bind, then you have an antigen-antibody complex. Okay. When a specific antibody binds to its corresponding antigen determinant sites on the antigen. If it's complete, have at least 2 antigenic determinant sites, 1 for each binding site on the antibody. Large antigens like bacteria may have millions of determinant sites. They might be haptens, which are partial. Do not have enough binding sites to bind the antibody. It may bind to a hapten in another carrier molecule. Okay, and then the response is triggered against the body cell carrier molecule. Either way, multiple ways to find some way to trigger that this is not mine. Okay. Here again are our antibodies, and that's again their immunoglobulins, and this is just to show you the specificity. IgG is 80% of all, and that covers most viruses, bacteria, bacterial toxins, things along that. IgE, when we talk allergic response, that's mast cells and basophils, and they kick out histamines, and that's what triggers watery eyes. Think allergies, watery eyes, runny nose, etc. And that's why when you take allergy medicine, it's an antihistamine. IgD on B cell surface, where it binds antigens and extracellular fluid, that's the humoral response, and plays the role in B cell sensitization to start triggering that B cell and T cell action. IgM was the first one, first class of antibodies secreted after the antigen is encountered. Its production declines as IgG goes up. Okay, anti-A and anti-B antibodies are examples. Okay, and IgA found primarily in glands, mucus, tears, saliva, semen, attack before pathogens gain an internal access. So there is antibody mediation before, as you can see, coming in those openings of the body, there are proteins that will, specific proteins that do look to stop pathogens before they get in. Okay, and this is what I want to show you. This is your B cell antibody mediated quick cartoon that should go along with your sheet. Here you go. Number 1, here's your cell, binds with the antigen. So it binds to, here's your B cells binding to the antigen. Okay, that activates the B cells, and you see this large replication of cells, okay, which differentiate into memory B cells. So you have that log that later on, when you get infected by that thing, that you can kick out the antibodies. These are long-lived memory B cells that then will remember what you were infected with. So the second time you're infected, that antibody production kicks in and you're at peak within 1 to 3 days. Okay. If it's the first time you're infected, this is a 2 week before you get this going. The other B cells differentiate into short-lived plasma cells, which kick out the antibodies. Okay. And I mean, it's rapid. And this is why you don't need to have all these floating, stuff for any time you get infected. The antibodies they kick out, once they do get into production, I think the number is like 2,000 antibodies per second or more, so that they can go, and you can see then they bind to the antigen. And this is what's going to bring in, complement proteins, NK, killer cells, killer cytotoxic T cells, all sorts of stuff along that line to get rid of those antigens. Okay. And this is how it does it. Neutralization, antibodies occupy binding sites on viruses and bacterial toxins, preventing them from affecting body cells. So that's one of the things they do. IgA antibodies and gland secretions cover bacteria and viruses, preventing adhesion and infection. You activate complex after they bind, and they can bind, accelerating that complement cascade and surrounding and killing of the pathogen. Of course, stimulating in the inflammatory response with released chemicals. Opsonization we talked about with some of that complement, and interferon is coating it with antibodies and basically that trigger. And then, of course, bringing in the macrophages to do their things and kill. Okay. So again, a work between specific and innate immunity. Antibodies are a signal. Okay. Then you can get precipitation, the linking of multiple pathogens by antibodies, creating an immune complex. When target antigen is on the cell surface, like red blood cells, you see agglutination. If you have given blood, this is what you see. They take a little bit of your blood when they're determining your blood type, and that's what happens. That's that agglutination. They put it in, and they put it in with the antibodies, and they see whichever one doesn't react and gel up and agglutinate is your blood type. Okay. Otherwise, the other pathogens have been surrounding, grouping, clumping it up. It's not healthy for you if you get the wrong the wrong blood type infused in you, because you do have that agglutination, and you're clogging the capillaries and having all sorts of issues. Okay. Here we talked about allergies, which you can develop or have naturally, or can develop over time. Anyhow, inappropriate or excessive immune response to the antigens. Those are the allergens. Okay. You get very sensitive and activate. It's kind of an over response of those B cells to the allergen. Then you get large quantities of the IgE. Okay. And that's when you see those allergic type mast cell reactions. Maybe inflammation, maybe pain, maybe itching, maybe all the above, a hypersensitivity. Okay, hay fever, other environmental stuff. It may be something you're allergic to in your blood. It could be a peanut allergy, food allergy. I have a lot of what's the word I'm looking for? Penicillin and medication issues, and you can cause anaphylaxis, which can be extremely dangerous and stuff by things that you may eat or drug allergies or things like that, and widespread mast cell activation and immune response that eventually could lead to respiratory and other issues as that anaphylaxis occurs. We'll talk more about that. The mast cells release histamines and other inflammatory results, and then again that anaphylaxis, either minor or it can be, anaphylaxis can be fatal. Okay. Exposures to the antigen triggers both a specific and non-specific. Neither branch works alone. The activities of each enhance the others, and we talk about that. I want to finish here shortly, not completely, but I do want to talk about the cell-mediated immunity, and then we'll do a little more at the beginning of next week. Here's the difference, okay? B-cell mediated is more about humoral and things flowing through the bloodstream. The T-cell mediated is more about Here I have engulfed a pathogen. And what you develop then is an antigen presenting cell, because these MHC markers have now, the macrophage doesn't necessarily have those, but because they've done the pathogen, now they are displaying those on their surface. And what you can see here is a little twofold. This is a helper T cell, okay? Of the three types of T cells, you have a helper T cell. Helper T cells are there to identify. One of the, as HIV and AIDS first came around and was understood and studied, what they figured out is all these people with an HIV infection and then acquired immune deficiency syndrome, was they weren't dying of the AIDS itself, they were dying of age-related issues, and they were very simple. Any child could knock them off, knock them out, very nondescript infections that every human, most every normal human would just not even half the time notice you had. And it was killing these people. Why? Because the infections, the HIV virus specifically attacks the helper T cells. So there's no identification. Okay. Because with the helper T cells, then you have what are called a naive, a virgin, a memory T cell. And these develop into the cytotoxic T cells so that they can bind and destroy that infected body cell. Okay. That viral pathogens are in, and they can destroy that and get it going through apoptosis. If you don't have that, you can't do that. Anyhow, and I want to show this other picture that you can see here, even in the cell mediated with my antigen presenting cells and the triggering of T cells. Notice you have a couple of different T cell triggers. One that is working on the cytokine, the killer T cells, and one that's activating B cells and memory B cells. Okay. Anyhow, we'll do this quick, and then wrap up and talk about more later. Here's a different type of T cells we talked about. Helper T cells ID the pathogens. The cytotoxic or killer T cells are there to destroy the infected body cells and the invaders and everything else. And then you have a suppressor T cell that needs to turn off the B cells, T cells. B cells are a trigger for the cytotoxic T to say, hey, the war is done, we're done, stop. If you don't, then over time, those cytotoxic T cells can just keep attacking your own self. So you do need some suppressors. Anyhow, that's plenty for today, probably more than plenty. Between your packet, and this is chapter 19 in your text, feel free to read up on some of this stuff. But again, you have an extra day this week. We'll get more into it, compare what we said to what you learned in the packet. Get some mental health this weekend, and we'll get together again next week and talk some more. Anyhow, have a great day. Stay healthy.